Greetings everyone. Today we are going to learn about NMR, which is nuclear magnetic resonance. So NMR is a special tool that plays a key role in structural elucidation of many organic and pharmaceutical compounds. In organic chemistry, NMR spectra can be used to identify a structure for which spectral interpretation is essential. By observing the number of NMR signals, one can approximately estimate the types of nuclei present in the structure. All nuclei cannot give NMR signal, but nuclei with spin quantum number I is equal to half can only win this game. Electrons surrounding a nuclei can oppose the magnetic field applied externally, thereby they reduce NMR signals. This effect is also known as shielding effect. But the effect of these electrons highly depend on the connectivity and orientation of the groups in the molecule. So what is NMR? NMR stands for nuclear magnetic resonance. So in presence of an external magnetic field, a nuclei can have different orientations. And what is the effect of this magnetic field on the nuclei? It is going to be studied in NMR spectroscopy. So in presence of a magnetic field, the nuclei can exist in two states. One can be considered as ground state and another one can be considered as excited state. And when we supply sufficient energy, the nuclei in the ground state jumps into the excited states, resulting in the absorption in the spectroscopy. So let us see a simple example here. So let us take ethane as an example. What are the nuclei present in this ethane? We can observe two carbons which are equivalent, that is, they are attached in a similar way, and it is also having another nuclei, that is hydrogen, and here all the hydrogen are equivalent because they are similarly attached. So ethane is having two carbons and six hydrogens. These hydrogens can also be called as protons. So it is having two carbons and six protons. But interestingly, here the carbon cannot give the NMR signal. On the other hand, the proton can give the NMR signals. So within the ethane molecule, two types of nuclei are there. One is carbon and one is proton, but only proton can give the NMR signal. The reason behind this is the carbon, which is 6C12, is having spin quantum number I is equal to 0, whereas the proton, which is 1H1, is having the spin quantum number I is equal to half. So in the NMR, the nuclei with I is equal to half can only give the NMR signal. So now if we take ethane is having 6 equivalent protons. Since all the protons are equivalent, they'll give a single peak in the NMR spectroscopy. But here, the proton can give the NMR signal when we apply the magnetic field externally. So when there is no external magnetic field, the nuclei will not have any spin, so the spin is 0. But when we apply a magnetic field under the influence of this externally applied magnetic field, the nuclei can have the two spin states. The spin in low energy can be considered as ground state, and the another spin state, which has higher energy, can be considered as the excited state. So under the applied magnetic field, nuclei can exist in either ground state or in excited state. And when we supply the energy in the form of electromagnetic radiation, this electromagnetic radiation will promote the nuclei from ground state to the excited state, which is observed as a signal in the NMR spectroscopy. So NMR spectroscopy is simply one type of absorption spectroscopy observed by the nuclei having spin quantum number I is equal to half. This situation can be simply illustrated by a common example. Suppose a person is working in a company 1, and unless there is no new offer, that person goes on working in the same company. And at one time, suppose a new company is going to be established, which is a big company compared to the company 1, and they have given an offer to the person. Now the person can jump into the company 2. So in order for the person to shift from company 1 to company 2, there should be some advantage. Suppose either the salary is increased or the designation is increased, there is a chance of shifting of person from the company 1 to company 2. So now that we can compare the situation to the NMR spectroscopy, the new offer offered by the big company is nothing but the magnetic field applied, and the hike in salary is nothing but the energy we are giving in the form of electromagnetic radiation. So when we apply the magnetic field, the nuclear will have two chances like ground state and excited state, but it can jump from the ground state to the excited state only when sufficient energy is applied, and it should resonate with the energy gap between these two states. So that is NMR. So what are the criteria required for NMR signal? So first is nuclei should have spin quantum number I is equal to half. Second is we should apply external magnetic field, and under this influence only the nuclei can have two spin states. And then third, we should supply energy in form of EMR that resonates with the energy gap. So for most of the nuclei, the energy gap resonates with the radio waves. So we can supply the radio waves as the electromagnetic radiation in order to observe the NMR signal. But here we can have a doubt that why the spin quantum number of the nuclei I should be equal to half in order to show that NMR signal. Now let us see what is the reason behind this. Let us first see what are the nuclei which has I is equal to half and which can give NMR signal. So nucleus consists of protons and neutrons. So the I value must be integer or non-integer, and it may have any value like 0, half, 1, 3 by 2 and so on. And we cannot assign the I value just by seeing that particular atom. Still, we can have a logic in order to remember which type of nuclei can have I is equal to half or 0 or 1. So suppose an atom which is having both even number of protons and even number of neutrons, then I will be equal to 0. For example, 6012, we can see that carbon cannot give the NMR signal. So it is because the I value of carbon is 0. So 6012 has 6 neutrons and 6 protons, so both are even. So we'll have I is equal to 0 and hence it will not give NMR signal. Second example we can take is 8016. So it is having 8 numbers of protons and 8 number of neutrons, both are being even. And similarly the nuclear which are having both number of protons and number of neutrons as odd will have I is equal to 1. So examples can include 7 and 14. So nitrogen is having 7 number of protons and 7 number of neutrons, being both odd, the I value will be equal to 1. Now, if the nucleus is having one of the component as odd and another component as even, for example, it is having odd number of protons and even number of neutrons, or even number of protons or odd number of neutrons, then I value will be equal to 1 by 2 or 3 by 2 or 5 by 2 and so on. So here all such type of nuclei cannot give NMR signal, because we have seen that for a nuclear to show NMR signal I is equal to half. So among these nuclei we can remember those nuclei which are having I is equal to half, so that they can give the NMR signal. So these examples include 1H1. So here we have 1 proton and 1 and 0 neutron. So similarly 6013, isotope of carbon 6013 is having 6 protons and 7 neutrons. That means it is having even number of protons and odd number of neutrons. And another nuclei is 9F19. So fluorine is having 9 number of protons and 10 number of neutrons. So it is having odd number of protons and even number of neutrons. Similarly 15P31, so it is also having 15 number of protons and 16 number of neutrons. So these are the examples of nuclei which are having either odd number of protons and even number of neutrons, or even number of protons and odd number of neutrons. So these nuclei can have I is equal to half, and these nuclei can only give the NMR signals. Here we should not confuse that every nuclear with one odd and one even can have I is equal to half, because when one is odd and another is even, they can have I value is equal to half or 3 by 2 or 5 by 2 and so on. And among these, only these nuclei can only have I is equal to half, can give you the NMR signal. So 1H1 is called proton NMR signal, and 6C13 is called carbon NMR spectroscopy. So I is nothing but spin quantum number. In order to see why I should be half, we can define another parameter, magnetic moment number, which is M, and it indicates the number of spin states of a nuclei in the externally applied magnetic field, where M is given as 2 into I plus 1, where I is the spin quantum number. Now let's take a case 1 where I is equal to 0. When I is equal to 0, what will be the M value? M equal to 2 into I plus 1, which is 2 into 0 plus 1, which give us 1. So when I is equal to 0, M is equal to 1, which means that the nuclear will only have one state, and this state of the nuclei can have the spin quantum number that is equal to 0. Let's take case 2 where I is equal to half, and then M is equal to 2 into half plus 1, so it gives 2. So now the nuclei under the applied magnetic field can have two spin states, and each spin state will have spin quantum with minus half as well as plus half. Now let us take case 3 where I is equal to 1. So when I is equal to 1, M is equal to 2 into 1 plus 1, that is equal to 3. Now the nuclei can have 3 spin states under the applied magnetic field. These spin states can have n spin quantum numbers as minus 1, 0 and plus 1. Now let us see why I should be half in order to show the NMR signal. Let's take case 1 where I is equal to 0 and M is equal to 0. Therefore, it will only have one spin state, and the spin of the spin state is 0. And in the case 2, I is equal to half and M is equal to 2. So now it will have two spin states. One of the spin state is plus half and another is minus half. Let's take case 3 where both of the states are equivalent and have different signs, so they are having similar magnitude but opposite sign. So such type of nuclei are perfect suitable for the NMR spectroscopy. So now let's take case 3 where I is equal to 1, then M is equal to 3. Now nuclei can have three spin states. I is equal to plus 1, I is equal to 0 and I is equal to minus 1. And here we can observe that all these spin states are not equivalent. So we can see that plus 1 is having some spin but 0 is not having any spin. So these spin states are not equivalent. They are not suitable for the NMR spectroscopy. Here the distribution of the spin is not uniform. So we cannot observe a perfect NMR signal in the case 3. So that now the nuclei under the case 1 where the I value is equal to 0 cannot give the NMR signal. Similar, the nuclei coming under the case 3 again cannot give the NMR signal. So nuclei which are having I is equal to half can only give the signals. So now let's see how NMR spectroscopy works. Suppose let's just take y-axis and z-axis, and we are going to apply an external magnetic field along the z-axis. And when we apply the external magnetic field, the nuclei can have one orientation such that its rotation is parallel to the applied magnetic field. So the state being parallel to the external magnetic field will have the less energy and more stable. But at the same time, the nuclei can also have another orientation where the nuclei will have an opposite rotation so that it is having higher energy and less stable. Now this orientation where the rotation of the nuclei is aligned with the orientation of the external magnetic field is called as the ground state or the alpha orientation, and I is given as plus half. And the another orientation which is having the opposite orientation to the applied magnetic field will have the beta orientation, and it is given as I is equal to minus half. So under the applied magnetic field, a nuclei can either have plus half orientation or minus half orientation. Now let us see how NMR spectroscopy works. In order to understand the NMR spectroscopy, we have to define few of the other parameters. So first is spin quantum number I. So we have seen that I should be half in order to show NMR. And second is spin angular momentum, which is S. Each spin state will have some angular momentum, so S is given by h by 2 pi into I. Third is magnetic moment number, M, and M is equal to 2 into I plus 1. Magnetic momentum, mu. Each spin state will have some magnetic moment, and the magnetic momentum mu is given by gamma into S, where gamma is the gyromagnetic ratio and S is the spin angular momentum. And finally, each spin state of a nuclei can have some magnetic energy, which is E, and it is given by mu into B naught, and B naught is the externally applied magnetic field. So by using these parameters, let's see how NMR works. So as we know that I should be half to show an NMR signal, so M is equal to 2 into I plus 1. If I is equal to half, it will be 2. So when I is equal to half, then the nuclei can have two spin states. So one of the spin state can have the quantum number plus I, and another spin state can have the quantum number minus I. So I is equal to plus half and I is equal to minus half. For each spin state, we can write the spin angular moment as well as the magnetic momentum. So S is equal to h by 2 pi. For plus half, it will be h by 2 pi into plus half. So after substituting, it becomes h by 4 pi. And similarly for minus half part, h by 2 pi into minus half will give us minus h by 4 pi. We can see that here the spin angular momentum of both of the spin states are equivalent in the magnitude, just different in the sign. So one is having the plus sign and another is having the minus sign. Similarly, we can also define the magnetic momentum. So magnetic momentum of this plus half spin state is equal to mu plus half is equal to gamma into S plus half, where gamma is the gyromagnetic ratio. So when we substitute the S plus half, it will be gamma h by 4 pi. So we should remember that for the plus half part, we have plus as the sign for both of them. And for minus half, after substituting, we get minus gamma h by 4 pi. Again, the magnetic moment is equivalent in the magnitude but opposite in the sign. By using these parameters, now we can define whatever the energy is associated with each spin state. So when we apply the external magnetic field, the nuclei can have two spin states, and one with the low energy is called as the plus half orientation, and another with high energy is called the minus half orientation. And when we supply the electromagnetic radiation equivalent to the energy gap delta E, then the nuclei can jump from the ground state to the excited state. So in order to see the energy gap between these two spin states, let us define what is the energy of the plus half state and the energy of minus half state. So E plus half is equal to mu plus half into B naught, because the energy is equal to the magnetic moment into the magnetic field strength. So after substituting, we get gamma h b naught by 4 pi. Similarly, for the minus half, we get minus gamma h b naught by 4 pi. So what is the difference between these two energy states? Delta E is equal to E minus half minus E plus half, which is equal to minus gamma h b naught by 2 pi. When we subtract this, the denominator becomes 2 pi instead of 4 pi. So here the energy gap between these two state is equal to minus gamma h b naught by 2 pi. And when electromagnetic radiation having the energy equivalent to this energy gap, then the nuclei can be transferred from the ground state to the excited state. So here the delta E is equal to h nu is equal to gamma h b naught by 2 pi. So the sign is not important here because we are taking the magnitude. So the sign negative will not be considered. If we cancel the h from the equation, then mu is equal to gamma b naught by 2 pi, where mu is the frequency of the electromagnetic radiation we have to supply in order to observe the NMR signal. So what is the law of frequency? So mu is equal to gamma b naught by 2 pi, where mu is known as the law of frequency, and it is also known as precessional frequency. Now let's see how the signals are measured in the NMR spectroscopy. Let us again take a simple example, ethane, and it is having the proton, which is having I is equal to half, which can give the NMR signal. But it is surrounded by another sigma electrons, and these electrons are negatively charged and the nuclei is positively charged. So these surrounding electrons can show some shielding effect on the applied magnetic field. Suppose we have applied a magnetic field B naught in one direction, the surrounding electrons can produce another magnetic field in the opposite direction. So now the magnetic field of the electrons is sigma into B naught. So the effective magnetic field B effective is equal to B naught into 1 minus sigma. So what is the applied magnetic field? So it is not completely converted to the protons because of the shielding of the electrons. But in the NMR, we are not measuring how much is the shielding of individual proton, but we are comparing the shielding with a standard that is going to be taken in the NMR. So in the NMR spectroscopy, we are going to have a standard like here, which have arbitrary value as 0, and we are going to observe the peak of the sample. Like let's suppose it has 2.1, and the difference between these two peaks is known as the chemical shift. So chemical shift is the shift of the peak from the standard reference peak. Tetramethylsilane can be used as a standard because it has high shielding, so it can have the chemical shift is equal to 0. So if a proton is having high shielding effect, it is going to fall nearer to the standard peak, so it will have less chemical shift. So the proton is then going to fall in the upfield region. Similarly, if a proton is having more deshielding effect, it can fall in an area far away from the standard reference peak, and that region is called the downfield. So the shielding effect is inversely proportional to the chemical shift. Higher the shielding, lower the chemical shift. Now let us understand this concept by taking a simple example. Suppose we have carbon-carbon hydrogen bond, and here this carbon cannot give the NMR signal and proton can give the NMR signal. Let us take another example where this carbon and hydrogen is attached with a chlorine, and we can also represent these structures as the Lewis dot structures. So here the first one can be represented by CCH. So here the electrons are shared equally between the carbon and carbon because both are having same electronegativity. But in the second example, we can observe chlorine, which is an electron withdrawing group. So because of the electronegativity, the electron will shift towards the chlorine, and this will generate the electronegativity on the carbon. So the carbon will pull the electrons that are shared between carbon and hydrogen, and this is negative inductive effect that is done by chlorine. So if we see the Lewis dot structure, the electrons shared between the carbon and chlorine are going to be shifted towards the chlorine because of the electronegativity of the chlorine, and this generates a partial electronegativity on the carbon which will pull the electrons towards the carbon. The electron density nearer to the hydrogen is reduced So now this hydrogen is getting the de-shielding effect. In this way, due to the presence of fluorine, the electron density nearer to the proton uh, is reduced by de-shielding effect. So we can conclude that higher electronegativity, then higher will be the de-shielding effect, and this effect will reduce the electron density, thereby chemical shift is going to be increased. So we can further conclude that higher the electronegativity, higher the de-shielding effect, higher the chemical shift.